let's look at hydroxide. Hydroxide is just going to look like this. Negative charge on the oxygen, it's got an extra electron. And so hydroxide ion. Water, we've seen before. Methanol, we've seen before, but I'll just draw it here again. Methanol is going to look like this. But these don't really show the three-dimensional. You don't have to show the three-dimensional shape. You know, water can be written in a lot of different ways. For example, here, if I write water like this, which is very common, or I could write water like this, which is very common. Either of these is fine. But what is the HOH bond angle? What would you predict the HOH bond angle to be here? 180. What would you predict it to be here? 90. So which is it? Is it 180, 90, or is it both, depending on how I draw it? What would the bond angle here be? What's that angle? 20 maybe? 30 degrees? What do you get? And so drawing it, I don't have to be accurate at all, you know, when I do this. And therefore Lewis structures we don't worry about it. But when we start analyzing the shapes of these, then we start worrying about it. And so let's take a look at some of these shapes here, like BCl3. If we look at BCl3, boron trichloride, boron trichloride is Lewis structure shown here. But when I look at this, and I think that doesn't, like boron, does boron have an octet? Boron doesn't have an octet here, so maybe chlorine should sacrifice to make an octet for boron. Does it? No. And so in this case, again, chlorine's like fluorine, it's not going to share. Oxygen turned out to share in the previous example, but there's just a lone pair here that's missing. But chlorine's not sharing. But anyway, what's the bond angle here? Is that 90? No, the bond angle here is 120. What's the bond angle here? It's not 180. You know what it is? 120. How do I know? Because I can't base the bond angle on the Lewis structure. I have to redraw this mentally in my head. When I redraw this mentally in my head, I think, okay, what is the EPG, electron pair geometry? The EPG is, there are 3 single bonds, so it's trigonal planar. And then I look at the MG, the molecular geometry, and I see the molecular geometry is the same, 3 bonded atoms. And so I get trigonal planar. And so this is the trigonal planar arrangement in BCl3. There's one thing missing here. What is it? One thing that I'd like you to include, actually multiple things in this case, but no, the angle's pretty good. The angle should be 120. Trigonal planar molecular geometry, all the angles are 120. The thing that's missing are the well, all the formal charges are 0. Otherwise, we'd include it. But for the 0 formal charges, you don't have to include this. The net charge is 0. If all the formal charges are 0, the net charge is going to be 0.
Pairs of electrons. The pairs of electrons.
Yeah, it's missing the lone pairs around chlorine. So I'd like to see those. They show them here, but they don't show them there. And there's one pair missing here. That's BCl3. Oops, this is pH3. pH3, this is Lewis structure. And so we can't tell the angles from Lewis structure. We have to analyze it first. And so to analyze this for the shape, we look at what the electron pair geometry is. So we have 3 single bonds and 1 lone pair. 4 groups, which means tetrahedral. But when we look, we only have 3 bonded atoms. If we only have 3 bonded atoms, then that gives us a trigonal pyramidal structure. There are 2 things I don't like about this structure. Do you know what they are? Sorry. Yeah, there's a lone pair here, which is going to push these down. There's going to be distortion, but undistorted, it should be what? the angle should be, the HPH angle should be. Well, no, tetrahedral sets the angle. Trigonal planar sets the angle 120. Tetrahedral sets the angle 109. And so the HPH bond angle should be 109, then it's going to be distorted by the lone pair. But the distortions are extra, you know. What we want to make sure is we get down the ideal angle undistorted here, 109. But there's one other thing that I don't like about this. There's no lone pair, it's missing here, and
The wedges need to be switched.
yeah, the wedge and dash needs to be flipped well. That's looking from below up. We typically don't look that way. We typically look from above down. Let's go to this one. H2S, hydrogen sulfide. What is the EPG for this? EPG is, well, we have 4 groups, 2 single bonds and 2 lone pairs. It's 4 groups, which sets the angle of 109. But when we look at the bonded atoms are going to be in a bent geometry here. 2 things I don't like about this. 1, this angle is much bigger than 109. We don't like that. And 2, the lone pairs aren't shown. We want to show the lone pairs. Those lone pairs are going to have an impact. And so the ideal angle is 109, but if you have 2 lone pairs, it compresses that by about 4 degrees, 2 degrees per lone pair. Here we have 1 lone pair, so it compresses about 2 degrees. So this is supposed to be 109, it's close to 107, let's say, and this is supposed to be 109, but we should be closer to maybe 105. If our distortions, you'll learn in Chem 1A more. We've got to look at the atom size and things like that. Okay, let's take a look at some of these here. We're going to look at hypobromite. We look at hypobromite. What's the EPG on bromine? Well, how many groups of electrons around bromine? 4. 3 lone pairs and 1 bond. That gives it what EPG? Tetrahedral. Now for tetrahedral, we only had 3 choices of structure. We had tetrahedral, trigonal pyramidal, and bent. But there's actually a 4th. The 4th is going to be linear. Whenever we have a 2-atom molecule, it's always linear. If we only have 2 atoms, it's got to be linear. And so this is also a tetrahedral EPG on oxygen, but this is a linear molecule. So it's linear. The EPG is not linear. The EPG is tetrahedral. The geometry is linear. So I don't know where they got this from. This is wrong. Now let's go to this one. What they did here was they didn't expand the octet on chlorine. They just left it as an octet. If they just leave it as an octet, what does that mean for the formal charge on chlorine? What is it? Plus 2. So the formal charge on chlorine is plus 2. These are all minus 1. The same thing, they didn't expand the octet on phosphorus. They just left it. So the formal charge on phosphorus is plus, and all the oxygens are minus. And that's what your book is going to do. It's not going to expand the octet to decrease the formal charge. It's not entirely wrong, nor is it entirely wrong to expand the octet to decrease the formal charge. The true reality is somewhere in between. And the true reality for this can be determined using a more sophisticated approach, which is called the full quantum mechanical treatment. What we're doing is the partial quantum mechanical treatment of these using Lewis structures, valence bond theory, and octets, and that kind of stuff. But up here, if we look, it's a tetrahedral EPG. There are 4 groups, just like up here, 4 groups. This should have been tetrahedral. Around chlorine, a tetrahedral EPG around the oxygen as well. But when we look around chlorine, it's going to be a trigonal pyramidal structure. So it's going to be something like this. We've got to invert these here. Phosphate is going to be tetrahedral, EPG, and tetrahedral MG, so we end up with something like this. So this is missing three things. It's missing the lone pair on the oxygens. These wedge and dashes are flipped, and the formal charge and the net charge isn't there. No, they do. And so we should get some practice doing that. And so how do I want it drawn? And so if I was going to do phosphate based on that Lewis structure, this is how I do it. So I'm not going to expand the octet, I'm just going to keep the octet and keep the positive formal charge on phosphorus. So I'm going to have one up and then one down to the right at a 109 angle here. And then I'm going to have one sticking out, this wedge sticking out here and the dash sticking. And so they have the flip. And then I'll throw in the oxygen here. And so the first thing is I need the lone pairs on the oxygens here. Now the lone pairs I'm not going to show for these, you know, if they're sticking out or sticking in or in the plane. Is that, if the lone pair were on phosphorus, then yes, I'd show it. You know, is it in the plane, sticking out, sticking in? Okay, then I write the formal charges in here, this, and then I write the net charge. So I add up all the formal charges, I give the net charge of 3 minus.